So yeah, I'm Dave Abrahams. That's in my script. I work in Adobe's Software Technology Lab, which was started by Sean Parent, with the mission to improve the code that people write through education, research, and tooling. And the first edition of the lab included some of my heroes, including Alex Stepanov, Matt Marcus, Paul McJones, and of course, Sean. So I'm really honored to be a part of this group. I'm also honored to be with you here today in Folkestone to talk about my current project, a programming language called Hylo. Now, I'll be honest, preparing this talk has been a challenge. I have not slept much in the last 3 weeks. See, I find myself at a conference for C++ industry practitioners giving the opening keynote about a completely different programming language that isn't even ready for production use. So I know you're probably wondering how any of this matters to the work you do every day. Well, first I'm going to tell you to ignore that. When I look back, the talks that have made the biggest difference to me weren't those with the most practical advice or tips and techniques. Those are all good things to get from a talk, but the talks I remember, the ones with the real lasting impact, have changed the way I think about programming. And I think Hylo could be a good vehicle for that kind of impact. So Ken Iverson's 1979 Turing Award lecture, Notation as a Tool of Thought, was about the way that the language we use shapes our ability to think. So before it was a real programming language, APL was just how he described algorithms. It was called Iverson notation. So that's an algorithm for finding prime numbers. So it goes both ways. Thinking shapes notation, shapes thinking. So I used APL when I was in high school, and I can tell you it was a mind-altering experience. I was lucky enough to work with dedicated APL terminals, which had these special keyboards. I can't imagine how you would do it with an ASCII keyboard, but those wacky symbols you see there aren't even the whole vocabulary, because you can overstrike them to make other meaningful combinations. So a programming language is a lens through which you can view any programming problem. And looking at the rest of the conference schedule, it's chock full of practical C++ specific content that your manager is sure to see as a good investment of sending you here, But you should use this talk to expand the perspective that you bring to the rest of the conference and that you carry back into your job. All that said, I'm not sure what you're interested in or curious about with respect to Hylo, and there's so much I could say. So please, if you have a question, raise your hand, and if I don't notice you, you can even shout, and I don't mind being derailed. So this talk was also a challenge because it was hard to find the beginning of the story. I found I kept needing to keep stepping back in time to explain the motivation for Hylo. And after pulling on the thread for a few weeks, I eventually found the beginning way back in 1995, 3 years before the first C++ standard. So I'd been working on this music notation software, and the implementation had gone through a couple of programming languages before I finally got a hold of the C++ compiler, which I'd been using for almost 2 years at this point. And this was in the days before the internet was a place to learn anything you wanted to know about everything. But my colleague Mark was one great source of information. He was always chatting me up about some cool programming idea. So one day, he drops this issue of Dr. Dobbs' journal on my desk. It says, "You've got to read this article." And it was an interview with Alexander Stepanov about the STL, his revolutionary open source library. Now, I know some of you in here probably don't even know what the STL is. I've met some really smart people who don't. But it's the library that eventually supplied the algorithms, iterators, and data structures for the C++ standard library. So if you're not old enough to remember this, imagine in 1995, C++ came with basically no algorithms or data structures. You had to roll your own. And what did that mean? Well, it meant they were wrong, right? They were also undocumented, and they were poorly designed. They were one-off efforts, right? Your job was not to build these general libraries. It was whatever, mine was to be a music notation software expert, which I was. But the STL was the opposite of that one-off thing. It was a masterpiece of coherence, and it came with clear documentation. It was the first real example of Alex's methodology, which he called generic programming. And unlike the object-oriented frameworks I'd seen, the STL was non-intrusive, which meant that you could sprinkle it into your program without rewriting APIs and adopting base classes. And there was something special about generic programming when it came to code reuse. I always sort of thought that the promise that object-oriented programming made for code reuse was never fulfilled. So for me, the STL was a total game changer, because now I had all of these facilities that were good at my fingertips. And it was more than just a tool, right? Using the STL idioms, its language, changed the way I approached programming. There was just one problem. If anything threw an exception during an STL operation, it was undefined behavior. So my program was already using exceptions to handle disk exhaustion, memory allocation failure, and user cancellation. And if that was going to break the STL, I wouldn't be able to use the STL. But to me, it seemed like this couldn't be that hard a problem. So I found Alex Stepanov's email address somewhere and wrote to him asking why it was like that. To my surprise, he wrote me back a really nice email explaining the situation. He said, first, the problem was unsolved because nobody knew how to fix it. And second, time was running out. The C++ standard was already overdue, and the committee was unlikely to make changes. But I thought it should be possible to apply the same principles that I'd been using in my own software to make the STL exception safe. Turned out I learned a lot during this process, but the long story short, I found STLport, which was a nice portable open source implementation of the STL, and I was able to add exception safety and contribute that back upstream to the project. But the bigger problem I faced was social. Lots of programmers, including committee members, were confused by exceptions, and they didn't know how to think about error handling in general, which left them suspicious and powerless. So it was straight up FUD. So to get changes accepted into the standard, I needed them to see error handling the way I saw it, as a normal part of programming. And I needed them to become powerful with exception handling. So I worked out a way to think of error handling in terms of 3 guarantees a component could offer to its clients. And that seemed to work. My changes were eventually accepted into the standard at the last minute, and that conceptual framework was the basis of some of Herb Sutter's writing on exceptions, and it's still reflected on the Wikipedia page for exception safety today. But this isn't about me succeeding at that. The point is, this experience of making programmers more powerful was kind of thrilling for me. So I began trying to repeat it and would eventually come to realize it had become my professional mission. So for example, when Beeman Dawes suggested we start the Boost Libraries project, I was all in because I'd seen firsthand how a well-designed library can open up new ways to think about solving problems. Now, Beeman passed in 2020, and he was living demonstration that collegial respect and kindness lead to great results. And his idea for Boost blossomed into a unique community of collaborative library designers because of the example he set. I've read that about 100 times over the last week. Never happened. Anyway, by the way, thanks. I miss Beeman. A lot. So, by the way, if you like the idea of open source, high quality, modern C++ libraries, you should check out beemanproject.org. This is a new effort aiming at producing libraries for the standard. So I started BoostCon as another expression of my mission, right? Sean Parent was our first keynote speaker. And in 2012, the conference was rebranded as C++ Now, and we had Sean back again. And this time, his talk wasn't just inspiring, it was one of those with a lasting impact. It changed the way I thought about software. It was value semantics and concept-based polymorphism. So I'd seen some of this before, but this time Sean gave more attention to value semantics, and that part really grabbed me. So I'll take you through his key points. First, like any good speaker, he defined value semantics, right? So he started out with this definition from Elements of Programming. A value type is a correspondence between entities with common properties or species and a set of values. So everybody understands what that means, right? I don't need to explain it. Right? No? Well, me neither. It turns out that value semantics can be really hard to describe in simple terms. So I've been obsessed with this topic for the last 12 years, and I think I only came up with something good recently. Anyway, I think I've finally boiled it down, and Sean kind of agrees with this definition. So it's about the independence of values, right? Value semantics is what we call the behavior of a type or a system that maintains that independence. And if the value of every variable of some type is always independent from the value of all other variables, that's a value type. So for example, that's true of an int in C++, right? We initialize x, and then we initialize y with x, and we print both variables and change y, and we print them again, and x is still the same. Ta-da! I know, right? What am I so excited about? This is totally unsurprising, right? And the same principle applies if I use a more complex type like vector. So to C++ programmers, the idea that dynamic arrays act like int is no big deal. But among modern languages, it's a pretty radical idea. So in Python, for example, if I do the same thing, I'll find that x and y have entangled values, right? So in fact, in C# or in JavaScript or in Java or Scala or many, many, many other languages, all mutable objects act this way. They have reference semantics. So value semantics is the absence of entanglement of variable values. Okay, so Sean went on to say why value semantics matters. He pointed out that reference semantics makes it impossible to reason locally about the effects of any mutation, because when you're mutating y, you could also be mutating x. Now, in this example, you don't need to look far to discover that x and y are aliases, right? But all you need to do is introduce a function call boundary, and then you can't discover that anymore. Now x and y come in as parameters, and there could be many call sites in your program. And to understand this mutation, you need to reason about all of them. And it doesn't stop there, because any of those call sites might just be passing along references from somewhere else, and so on, and so on, and so on. So maintaining code gets really painful when you have to go on a journey researching consequences just to make a change. How many people here, is that like a normal part of your job, maintaining a large piece of software? Quite a few. I can tell you, Photoshop is, Sean talks about it, 30 million lines. You can imagine there's a lot of this. There's a lot of that kind of researching consequences. It slows us down, right? It slows down our development. That's why taking away local reasoning is just about the most disempowering thing you can do to a programmer. So Sean also talked about the importance of value semantics for concurrency. So when Rust programmers talk about fearless concurrency, they mean that a program that passes the borrow checker can't race. But you don't actually need a borrow checker to get that. All you need is strict value semantics. It's simple, right? If mutable state is never shared, then it's never shared across threads. So you can't have a race by construction. Finally, Sean described a relationship of value semantics to pure functional programming. So FP zealots will tell you that to get local reasoning and thread safety, you need to ban mutation, right? And that is one path to value semantics, because you can't observe changes to one variable through another because there are no changes, right? And if you start out assuming that the world is full of shared objects, banning mutation is probably the only way to get the properties we need to program reasonably, right? So in pure languages like Haskell, there is no in-place mutation. To work with a new value, you build a new object, right? And in languages with rampant sharing and mutation, like JavaScript and C# and whatever, the new hotness is to discourage mutation and build whole frameworks around the idea of immutability. This is just a few articles I pulled off the web about why immutability is so important. All of these reference semantic languages. But immutability clashes with the real world in a couple of ways. So first, the underlying machine has mutable memory, and you can't get performance unless you use it. But it's a lot to ask of an optimizer to take code that's written to do this, creating new objects every time, right? And make it do this instead. Also, immutability clashes with our mental model of the world, right? We live in a world where things can change. Put that down, we'll put it back up, right? So, for example, this wonderful paper by Melissa O'Neill is all about how hard it is to implement the sieve of Eratosthenes in Haskell. That's one of the oldest known algorithms. But instead of blaming mutation, value semantics elevates it, right? But keeps it from propagating into locally unknowable values, right? We get most of the benefits claimed for pure functional programming without the costs. So Sean made all of these points while building a mock-up of the essential parts of a serious application using only value semantics. And he explained how the core of Photoshop was actually based on these principles. So that left me with this insight, that you can build real software using pure value semantics. For years before this, I kind of thought Sean was being kind of extreme, you know? But then when I considered all of Sean's points, like the importance for thread safety and local reasoning, the importance for generic programming, which as far as I could tell was the path to code reuse, and how mutations in the machine model and our mental model, I began to realize that we weren't going to succeed at building reliable software at scale unless we used pure value semantics. So C++ supports value semantics, right? He did his whole demonstration that way. This is a rare and valuable thing, a forgotten wisdom from languages like Pascal and Ada. For 30 years during the OO revolution, almost every language was based on references, and many still are. Unfortunately, though, C++ also undermines value semantics. And it does it kind of indirectly by achieving independence through copying. I'll show you what I mean. So if you take this into a code review, the first thing someone is going to tell you is to pass delta by const reference, because what if it turns out to be a big num or a large matrix, right? That could be expensive. So you make the change. And it makes total sense. Pass by const reference has become the C++ way to say pass by value, just do it efficiently. Right? Can we all agree that this is still a bog standard correct C++ code? It's pretty normal, right? But let's look at what happens when we build up a program this way. I'm going to write similar functions, a similar function that uses the first one. And this might not be the most efficient implementation of adding 2 times x, right? But it's equally correct, yeah? We're using the sort of standard idiom. Finally, let's test this on an int. So x is 3, and we want to offset it by 2 times x. So what does this print, anybody? Well, if everything we did was correct so far, it would print 9, right? 3 plus 2 times 3. But it prints 12 because every time we offset x, we're also offsetting delta. So something is very wrong here, right? Even if you think offset by and its documentation are okay, it's clearly not composing into offset to the way functions are supposed to. So how would you change the documentation to account for this case? It's kind of weird. Personally, I don't think you can without making the description so complicated as to be useless. I think the very best thing we can do is to make it a precondition violation if the things overlap. Right? Now we still have a simple meaning, right? It's still offsetting x by 2 times delta. So these 2 preconditions are just trying to achieve independence. And it's not specific to these functions. It kind of hit me like a ton of bricks when I realized this. Without independence, the effects of any mutation probably can't be specified. So if you think about it, you're mutating your parameters, and you can talk about that in your documentation. You have names for those. But you're also mutating some other stuff that's entangled with them, and you don't even have a way to describe that stuff. Right? So every mutating operation really depends on independence for its correctness. But have you ever seen an independence requirement documented like this? I haven't. So why do you think that is? So I think it's because we just assume that references are accessing independent values. That's our mental programming model. And most code works because people seldom violate these assumptions. Now, a lot of us think of making assumptions as a bad idea. So why do we make this assumption? It's because we have to. It's the only way to make sense of software, right? Especially at scale, is by hook or by crook, creating a mental framework where we can reason locally. Okay, so cut yourself a break for making this assumption. So when we use references, we mean value semantics. But the compiler has a very different view of the world. It has to play by the rules in the standard. So it would be nice if we could just not worry about it. But the fact that value independence isn't enforced by the compiler introduces this niggling uncertainty about correctness, these undocumented preconditions for edge cases that almost never occur. Those are some of the worst kind, because you worry about them, you try to program around them, and you wonder if you're wasting your time. It also hurts efficiency because the compiler has to reload data from memory because it has to pessimistically assume that there is overlap. Again, to support these edge cases that almost never occur. So, despite these compromises to value semantics, C++ is a great language. A lot of the greatest software has been written in it, so why did I move on from C++? Well, around the time of Sean's keynote, I'd begun to see that C++ wasn't a great vehicle for my mission. to empower programmers. And the first reason may seem obvious. It's just too difficult. So this quote from Bjorn actually touches on all of the issues one way or another. He says that C++ has become too expert-friendly, but that rather than dumbing down languages, we should educate more experts. Of course, it's hard to argue with the implication that C++ is too complex and error-prone for non-experts. He didn't come out and say that. That's what I think he meant by expert-friendly. And as an expert in 2012 myself, I don't think C++ was actually that friendly to me. I could make it do amazing things. This is familiar, yeah? Yeah, you have amazing power with C++, but it's a battle. So I could make it do these amazing things, but I was spending an awful lot of energy caught up in minutia instead of directly expressing my intent. And I think it's still like that for experts today. I asked Sean about what slows down his development. He had a long list. Rule of 0, 3, 5, 7, pass by value versus reference versus universal reference, getting all of the iterator requirements right, when to use move and forward, and being sure not to use an object after move or forward, when to use no except, and on and on. So, yeah, I think expert-friendly is a fallacy. That's what we say when we don't want to admit that it's just unfriendly. I disagree with the implication that to make a language easier, we have to make it dumber. It seems to me that a smart language design could make programming easier for everyone. So lastly, like becoming a C++ expert, I wasn't all that interested in educating people into being C++ experts anymore. That's an all-consuming job, and it's not directly, targeted at empowering programmers. Just being a language expert doesn't make you a great programmer. So next, addressing the problems I saw with C++ would require large-scale changes and long-term planning. But after years of trying, I'd failed to even interest the C++ committee in establishing some principles for evolution, any principles. Okay, and last of all, generic programming story was bad and not likely to improve. So that might sound outrageous to you because like C++ is where generic programming became a thing. Let's get it from the horse's mouth. Alex gave this seminar called STL and its design principles at Adobe 22 years ago, before he even worked there. And this is where he met Sean, actually. It's a fantastic talk. You should watch the whole thing. But I'm just going to show you an excerpt where Alex talks about what generic programming is like in C++ and what it should be like.
Do you believe that I know STL? I think it's sort of self-evident that I do, right? My son, who is a junior at UC Santa Cruz, was taking a C++ course. And he needed to do some STL five-line drugs. Comes to me. He couldn't do something. I said, no problem. I sit down, I type, I compile it with his compiler, and I run away in horror. Why? I get 5 pages of error message. Right? I didn't know what to do. I say, okay, it's your class. No one was right. Right? I'm not paid to read through 5 pages of his error messages. Does it happen to you? Of course it does. It's awful. Why does it happen? So the fundamental thing is that there is no specification of the interface. Okay? When I say that something is an iterator, it's just a word.
Okay, so there's no specification of the interface. And I know what you're thinking, right? Since C++20, we have concepts and interfaces are specified. I express the input iterator requirement in the language now. It's not just a word. So just hang in there because I don't think he's saying what you think he's saying. What happened to my sound? Crazy. Okay, tech people.
Of course, it's very ugly.
All right.
The tightening, it's a related trade.
They're going to back up. Ooh.
So let's look at the piece of code. This is real code. It actually does work. This is written in C++. It's a wonderful piece of code. It compiles, it runs, it works. Of course, it's very ugly. It has this tightening, it's a related traits, and puts it to related colon value type. And I cannot defend that. It is an elimination. No way you could write it different. There is one fundamental problem with it. If you compile that, you don't know whether it's right or wrong.
Okay. If you compile that, you don't know whether it's right or wrong. So remember that. Alex is worried about the experience for the author of this function. And now he's going to talk about the downstream consequences of that experience.
This is a bug. And I'm not going to ask you to find the bug. I'll show you the bug. The bug is here. Do you see this operation? Less than. It's not defined for input iterators. It's just not defined. I mean, you cannot look at 2 points, say, in a linked list, figure out which one is that. I don't know how to do it, no, but it's not defined. Will it compile? Of course it will compile. Will it debug? Yeah. For as long as I'm debugging it, random access iterators, it will work just fine. If I fast forward, it works. Defined for pointers. So for 10 years, it works. On the 11th year, somebody decides to use it. This is a simple example, but true, it happens all the time. Somebody decides to use it on a linked list. Finally, somebody tries, yeah? And what happens? He gets error messages he will never understand. Because he's using reduction, which he knows is a well-written component that has been used for 10 years, on a linked list, well-written component, used for 10 years, and then he gets error messages which basically say that something or other is not defined on some nodes. This is the...
Okay. So I know what you're thinking. Concepts are supposed to make error messages better, right? Wait. So back whenever he gave this talk, the consequences of getting this wrong are really bad, right? So Alex isn't worried about what happens when an end user makes a mistake with a correctly written generic component. He's worried about being able to deliver that correct component in the first place. And, he composes algorithms. So one component built on another, there's a lot of opportunities for error. If input iterator, when he says it's just a word, he's saying if input iterator wasn't just an identifier, but instead some code that had meaning to the compiler, he's assuming the compiler would stop us from using an undefined operator, right? In the same way that saying something is an int will stop us from calling a method on an int, because we specified in the interface, in code, that the thing is an int, normal type checking. But I can constrain this template with C++ 20 concepts all day long, and it will still compile. And the consequences for the downstream user are still just as bad. The user who passes a list iterator is satisfying the constraints after all. It says input iterator, right? They will get exactly the same message as before because the error is in the algorithm, and it has to point to code that they know nothing about, because that's where the error is. Okay, so this feature is doing nothing at all to help generic programmers get it right or to protect users from those mistakes. And in 2013, I already saw this feature was in the pipeline for C++. And since generic programming was so important to me, facility with generic programming was one of the powers I most wanted to help people with. And it looked like generic programming in C++ was going to remain treacherous ground for decades. So I was ready to move on. So at this point, I joined a team at Apple, working in secret on the language that became Swift. So my main responsibility was the standard library, but I also contributed a bit to the core language design. I highly recommend that you try using Swift for real work if you can. So like I said earlier, every programming language is a lens, and working with Swift after being steeped in C++ really opened my eyes. I got a new appreciation for safety, and I started to see that many of the ideas that I'd internalized as truths about programming were really just artifacts of the language I've been using. So I think Swift is a great language, and that's not me taking credit. I was part of an amazing team that brought diverse experience and insights to the table, and I'm really genuinely impressed with the results. I don't have ties to Swift development anymore, but it's the language that I choose to write code in because it lets me express my intentions cleanly, correctly, and efficiently the first time around. And naturally, the Hylo compiler is written in Swift. Anyway, there's one part of Swift's core language that I do take some credit for, and that's its deep support for value semantics. Because I was the person on the team who insisted that built-in strings and collections needed to be mutable value types. And that ended up driving some language features that take value semantics in Swift beyond what we can do in C++. Swift has real guarantees of independence. And Hylo owes a huge debt to the foundation laid by Swift value semantics. We'll see more about that later. Unfortunately, though, Swift's value semantics is also compromised. Because although it doesn't have references like C++, it does have reference types. So we didn't really have a choice about that, since Objective-C classes have reference semantics, and seamless interop with Objective-C was basic design requirements. So in new code, it's not that hard to avoid or isolate these classes, but lambdas, we call them closures, those also have reference semantics in Swift for complicated reasons. So for most types, Swift's independence guarantees are upheld by the compiler. But whenever reference types are involved, Swift uses expensive runtime checks that abort the program if violated, okay? And that's very similar to what Rust does when you have shared objects in Rust. Where was I? So those dynamic checks are expensive. They're expensive enough that making them thread safe would have been prohibitive. So instead of getting thread safety by combining value types, value semantics, and dynamic checks for reference types by construction, Swift has an additional system called actor isolation for ensuring thread safety. So that's just another layer of complexity. Not everything is perfect in Swift. So by the time I got to Google Brain in 2020, I'd started to fantasize about what it might be like to have a language that didn't compromise on mutable value semantics. And my team there we were all very obsessed with value semantics and that question. One of the first problems we had to solve was to try and nail down what we meant by value semantics. So I was still working on it then. We finally landed on a workable definition, still more complicated than what I showed you, but we posted it to the Swift forums, and there was a good discussion. Right around that time, Dimi Racordon posted on the Swift forums about the completion of her academic research project, which was called Featherweight Swift. So it was a common CS research activity, is distilling the essential properties of a language down into a tiny featherweight version and proving properties of that. This was, I was really psyched about that because we were trying to understand the properties of value semantics, and a formal CS approach, could shed some real light. But when I read the post, the first thing I noticed was that Featherweight Swift was purely functional, which meant no mutation. So, well, if you don't have mutation, every variable is trivially independent. And while you can say that's value semantics, it's pretty uninteresting. to me, support for mutable value semantics was the really unique feature of Swift's type system. And so it didn't seem like this was quite capturing the essentials. So I pointed that out with some trepidation because after all, it means, you need to start over. And to my surprise and delight, Dimi was totally into it. So I just went back and reviewed that thread, and at least for a language nerd like me, it's really fun to see that conversation happen and the people of different backgrounds sort of converge on a common understanding. Anyway, Dimi started to work with my team at Google on our research into value semantics, and we ended up publishing several papers together. Because it's what language researchers do, she had been bringing up a toy language she called Val to test our ideas about strict mutable value semantics. And between us, the ideas just kept coming until we began to think that maybe we could grow Dimi's little language beyond the toy stage and it might become a useful production tool. So we started a public project on GitHub for it and even had a cool logo. But last year, some less than cheerful lawyers sent us a letter. Apparently, their company holds a trademark on that name. So that was also a robotics language that was started in the 1970s. Anyway, that explains why some older talks and articles about Hylo use the name Val. Okay. So as a way into the world of Hylo, I went through lots of revisions of this, starting with C++ code, because that's what I figured y'all are familiar with. So here's a simple sort function that works on a vector of n and just dispatches to std sort. Okay, and so for testing, we declare a vector and we sort it with a lambda. Now, notice that some incredibly unrealistically conscientious person has actually documented that S and compare need to be independent. Otherwise, if they're not independent, this call to std sort would probably cause undefined behavior. So let's create statically enforced independence so we can delete that line of documentation. Okay, so first we need to remove the reference from our argument and then return the same type that we were mutating. And if our return type hadn't been void, we could package the result into a tuple. And now we actually have to return the sorted thing. We can fix the documentation. And now we can drop this requirement. And finally, the call site needs to change. We need to reassign V. So this form is what's known as a functional update. And there's a general transformation you can use on any mutating function. Of course, because this is C++, there's one more thing we have to do to make it efficient, right? Move that thing. Of course, no one's going to do all their mutations using functional update form because it's a hassle. But pass by value is part of C++'s built-in support for value semantics. And we're leveraging it here to do mutation with true independence. So, but all of this rewriting is a pain. So suppose we had a language feature that would give us efficient functional update semantics with the move and everything else, but avoid reassignment syntax. I'd call it in-out. So let's replace that reference with my new keyword, in-out. And then the compiler would rewrite my declaration of sort to use pass by value and return the updated result, and it would rewrite my call to sort as a functional update. And there'd be a matching convention called in for doing pass by value without a forced copy, right? Or you could think of it as pass by const reference with independence. Okay, so that looks like this. It's an in keyword. So the only other thing you need to make all of this work is a law of exclusivity, where the compiler doesn't let you pass an in-out argument unless it can prove that it's the only access. This law was coined by John McCall from the Swift team. And he's going to keep coming up over and over again in this talk because he did many amazing things for value semantics. So this is the original example, except using in, out, and in instead of references. And if you use it and you have a compiler-enforced law of exclusivity, you get an error right here where the problem originates. Okay. So those moves may be a concern for y'all. But let me point out there's a virtuous cycle at work here. So in, out, and local variables don't need to be moved to be unique because they're already unique, right? So they can be forwarded to in, out directly, or to in as references, right? Ins can be forwarded to in without checking. So the extra local reasoning means you can have confidence in your code and the compiler can optimize better. And if you take this all the way up to the root of your program, what I've just shown you is the basis for mutable value semantics in Swift, in Rust, and in Hylo. So all three languages are circling the same target of performance, safety, and value independence. They use different keywords, but it's the same base model. So keeping these as just parameter passing conventions allows the compiler to easily ensure independence and control lifetimes so that it can ensure safety because it knows the source of every reference. All the references are formed inside of a scope where you know the source and they can never escape that scope because they're just parameter passing. But there's one problem. How do you handle mutation through computed parts? So like a subscript. So when you subscript an object, you're notionally accessing a part of it computed from the subscript parameter, right? And in this example, we have a 2D vector with x and y components, and the subscript is allowing us to access them by number. X is coordinate 0 and y is coordinate 1. But notice that returned reference. That doesn't have any of the nice static guarantees we get from the compiler for our passing conventions. So if the compiler could give us those guarantees with an ordinary reference, C++ would already be a safe language. Okay. Rust has an answer to this problem in something called named lifetime annotations, where you use these names beginning with the apostrophe, or as we say in Hawaiian, the okina, the glottal stop, to describe the relationships between the lifetimes of parameters and return values. So named lifetimes become generic parameters, and then they proliferate through the type system, showing up in error messages that frequently baffle users. Among Rust developers, I don't know if you've heard the term fighting the borrow checker, but that's a meme. And these are a big part of the reason. I think it's quite telling that the concrete type stir, its iterator type, has a generic parameter, right? That's a lifetime parameter. And that's all because the iterator type has to refer to the stir. So it's got an embedded reference. So somebody has to track that relationship. So returned references are a very costly abstraction to have in terms of language complexity. Swift has a brilliant answer to this problem that avoids all of that complexity. And there's an initial approach, it's a very simplistic initial approach in Swift was to use getters and setters. And so this is a Swift translation of the C++ type that we just saw. So you notice that bundling the getter and setter together, that avoids creating an overload set and gives us one entity to document. Okay, let's see how it works. So this is a pure read, so it just calls the getter. And this is a pure write, so it just calls the setter, right? And a read modify write puts the result of the getter into a temporary and applies the mutation and calls the setter to put it back. And this works as long as all types are copyable. And they were all copyable in Swift until very recently. But the performance isn't great in general. So if you just switch to Swift's dynamic array for this example, and now we can test it with an array of arrays, and let's just focus on the read modify write case. First of all, you've got two bounds checks, right? And that's because we lose the context that we acquired in the getter and have to reestablish it in the setter. It's the same thing that happens when you return a reference, right? You lose the context. But worse, you have to copy an inner array out for modification, and then you have to assign it back in. So that's really expensive. So John got to thinking about this problem, and he realized he could write a function that applies an arbitrary mutation without ever losing context, letting a reference escape or copying the target. So let's just make some space. So the mutation comes in as a lambda. That's what that is in Swift. And we just call it, right? And then we could manually rewrite the access site this way, right? So we're calling the modify function with we're passing the index to be modified and a lambda expression that performs the modification. And now everything is phrased in terms of in-out parameters being passed down the call tree. There's no loss of context. So control goes from the caller into modify, and then there's an inversion of control back to the caller via the lambda, after which we're back to modify, and finally that returns to the caller. Okay, and so when we use this approach for subscripts, instead of calling a function, we express that inversion of control as a yield, which looks like this. So in fact, Swift compiles the code using an LLVM coroutine primitive rather than literally passing a lambda, but the meaning is exactly the same. And now we have our nice call syntax with safety, efficiency, and no lifetime annotations. I think this approach is absolutely brilliant, and we make heavy use of it in Hylo. Also note that there's a place for code after the modification occurs. Now, that arrow wasn't supposed to disappear on you. Right after the yield. The fact that we always come back to an accessor means we can project something out that doesn't exist anywhere in memory because we have a chance to update the data structure based on the new value. So, for example, the accessor for a bit vector, which is the classic vector of bool case, could look like this. Right? So that highlighted code is the code app that we come back to after the yield that updates the data structure. And in C++, doing this sort of thing means exposing a proxy reference, which is at best a leaky abstraction, and frankly, I just think doesn't work. In Swift or in Hylo, though, the caller experiences a bool as just as real as if it had been stored that way in the first place. Okay, drink break. This is going a lot faster than I thought. So, Hylo is focused on two ideas: value semantics and generic programming. And these four phrases on the left serve as sort of touchstones for me when I'm thinking about what Hylo's like or what we hope it will be like. And the first two are very concrete. Right? Fast by definition means we're trying to make our object model and our calling conventions be efficient before any optimization kicks in. So the optimizer doesn't figure out how to make costly abstractions fast, like, you know, the immutable to mutable transformation. That's really difficult. And we're trying to make it highly optimizable to give it the best possible chance. So those independence guarantees actually mean that the compiler can assume there's no aliasing, for example. Also, we're shooting for a transparent performance model where costs are predictable and reasonably obvious in source. Safe by default is a point in the design space for languages that's occupied by Swift and Rust, possibly among others. Does anybody else know a safe by default language? Another one? Okay. Well, so what it means is there's no possibility of creating undefined behavior except by using an easily identified and audited subset of the language. So something that, it appears visibly in the code. In Rust, there's actually an unsafe keyword that you have to use in order to access unsafe operations. So in your code reviews, you can find that and say, okay, I need to check this to make sure it's actually correct. The language still provides sharp tools like the ability to dereference a pointer in the unsafe subset, and it encourages you to use those things to build safe abstractions. So you can build a safe abstraction out of unsafe parts. You would have to be able to, the underlying machine is unsafe, right? So there couldn't be any safe things if you couldn't do that, right? So Swift's built-in array is built out of pointers and dynamic memory allocation, whatever. Okay. The last two ideas are more qualitative. So normal by inclination means that we don't want the programming experience to feel exotic, right? It should be a good match for the intuitions of users, and we're especially vigilant about not including anything we think could turn out to be surprisingly difficult. Expressivity is an important thing, but it's not at the expense of being explainable and understandable. For example, it's a non-goal for Hylo to support higher kinded types for the foreseeable future because nobody can explain what a monad is, right? It's commonly said that you only really understand it when you can't explain it anymore. We're focused on understandable code, local reasoning. Okay. Simple by design. Since I have a moment, let me be more specific about what I mean by that. If you give me a generic algorithm constrained to monad, I don't know what that does because monads can be so many different kinds of things. They all have these properties. What does it mean to leverage these properties? There's no unifying idea there. All right, so I've never seen an algorithm on monad that I could understand. I know they exist. I wouldn't know how to use it. Okay, simple by design means that we're paying close attention to the overall language complexity and coherence. So whatever the benefits, every language feature is a new wrinkle in the surface people have to interact with. What's your use case is the first question we ask. And then we ask whether that use case is important enough to justify the complexity cost. Saying no is a really powerful thing. I don't think the C++ committee is saying no nearly enough recently. I actually think Swift has started to not say no enough. Swift is growing quite quickly. Got to be careful with that. Okay, some specifics. So we like Swift, so we started there. Rather than reconsider every design decision from the ground up, it made sense to start with a language design that we know works for people. And as we've seen, it has some important features for value semantics, which is core to our design goals. So next, we focused on fundamentals first, the object and function call models and argument passing conventions. Oh, you know what? My timer probably got interrupted because I exited the slide presentation. Can somebody in the back tell me what time I'm at?
We've got like 15 minutes.
Okay, thank you. Somebody in the front would tell me that. Go to the back. Okay. So we focused on the fundamentals first, right? The object and function call models and argument passing conventions. The design also weaves generic programming in at the lowest levels of the system. And I think that's probably common for Swift and Rust too, because things like movability and for loops end up depending on declared conformances. So just being able to do the generic system becomes like part of the base system. And that's one of the challenges. When I asked Dimi what things that she thought was most challenging about developing Swift, that was one of the things there. The core is not, developing Hylo. The core isn't small, right? There are a lot of languages are built up from a tiny core. Like if you want an extreme example, think about Forth. But you can't do that with Hylo. Okay, so engineering is all about making trade-offs, and language engineering is no exception. So here are some of the trade-offs we made, and I was going to delete that last line with the blank. I don't know why it's still there. So the winners of these are on the left. So for example, we implicitly move out of an object on last use. And that's much more important to us than predictable destruction order. We don't think, like, we think about, do we ever count on destruction order? Not unless we're using RAII, right? RAII meaning an object that's supposed to, something that we want to run at the end of scope, right? There's an actual feature for run at the end of scope in Swift. It's called defer. Right? I think if we want to do that, we should just use a feature for that and not try to hijack destructors. So the ability to elide moves is more important than the ability to observe side effects that you code into your moves. And again, about moves, like we have these markers for L value moves in C++, right? We write std move. Well, that might be important for C++ because it leaves behind an empty shell, right? In which you have to be conscious of. Since we have destructive moves, that's not important. So we don't think like being able to see your L value moves is important. We prefer noise-free correct code. Implicit conversions, totally not worth their weight. I program without them all the time. They cause a lot of complication in the language. Okay. Full type checking of generics and intentionality is more important than any conveniences we get from duck typing, for example. So let's talk about generic programming in Hylo. I should say off the bat that the basics of generic programming model are the same in Swift, Rust, and Hylo. The most glaring difference you'll find with Rust is there are no lifetime annotations, which tend to get into everything once you let them into the language. So interfaces, concepts, are described by traits. I know we have this other word in C++, trait, doesn't mean the same thing at all. So a trait fills the same expressive role as a concept. It describes the constraints on a type. So the body of a trait declaration lists its requirements, right? And this one says that for any integer type, there's an associated unsigned integer type that can represent the absolute value. That's the magnitude type. And then this one says there's an abs method that gets you the absolute value. By the way, this is just a tiny sketch of a piece of integer protocols. right? It's not meant to be a complete example. So we have this associated magnitude type because the minimum value of a signed integer has an absolute value that it can't represent. So you need to go to an unsigned type. So obviously, right, this is just a small demo. So you can declare that one trait is a refinement of another. We use inheritance syntax. It's just like, declaring class inheritance. So to be a signed integer, in addition to the integer requirements, you also need to supply a negation operator. So if we assume here that int is declared somewhere else and already has a unary minus implementation and a less than operator, then this conformance declaration satisfies the remaining requirements for conformance to signed integer. So unary minus is picked up from int automatically wherever it's defined. So this is a post hoc conformance declaration, which means that this thing could appear anywhere, maybe even in a different module from where int is declared. And here's the unsigned integer trait. It doesn't add any requirements. And that's kind of unusual. You might wonder what that's good for. Well, just like we can extend a type post hoc, we can extend a trait. And if you extend the trait with implementations that match requirements for the trait, they become the default implementations of those requirements. So the default magnitude type for an unsigned integer is just itself, and the abs method is just the identity. Okay, and if I wanted to, I could provide a specific implementation of that requirement for the conformance of uint to unsigned integer. This one is just adding some instrumentation. So I hope this all looks like normal programming. Yeah? It's a lot like what you do with your virtual functions, I think. Right, that overrides the default. And if I leave something out that I was supposed to provide, I get an error message, like you'd expect. Okay, let's get slightly more advanced. This is a conditional conformance. I'm saying that array is serializable when its member type element is. And now I'm going to write that serializable requirement for serializable arrays. Okay, so this is, if you map this back into C++, this is a generic function over arrays where they have a serializable element. But there's no angle brackets. So being able to use methods as post hoc extensions is really powerful for eliminating complexity in code. Users have a lot easier time looking at this and thinking about it than they do thinking about a generic function. It just looks like a method on arrays because it is one. Okay, so here's an excerpt of the standard library's collection trait. You can see it has a position type that you can subscript it with and a start and end position. So it's very like C++ collections, but you don't dereference an iterator because that would be an escaping reference. Okay, so now let's write std find, which is available whenever the element is equatable. So this is a generic algorithm that we write as a method, right? Just looks like plain code. Note that there are no const, non-const iterators, and mutability is determined by the collection that's being subscripted. And that design was actually forced by the combination of strict value semantics and safety requirements, but it works really well. So just to show you what a more complicated algorithm looks like, this is stable partition. So first it counts the elements, and it forwards that result onto stable partition n, which after dealing with the trivial cases, then it does these fancy looking subscripts. All right, so these subscripts project a slice of the array. First the slice up to I and then the slice from I to the end. And those slices are collections too, so we can just call stable partition on them. And then you all know what happens next, right? That's a rotate. Okay. So I think this compares really favorably with the readability of any other implementation of stable partition. Quick notes about concurrency. The concurrency effort for Hylo is led by Lucian. He gave an excellent talk, although he said it's a hard talk. He says that right in the talk at ACCU this past year. I'm going to shamelessly steal some of his slides in a minute, just a few. But you should go look at his talk if you want more details. But there's some basic principles that we're trying to achieve. So one is no function coloring. So I don't know if you all are familiar with the what color is your function blog post, but it's basically about like all these async await systems where you have to declare anything that's async up front as being different from an ordinary function. And then you have to use a keyword to await on it. And when they introduced that into Swift, by the way, and when they were doing that, I was looking at these calls to await, and I realized they're not saying anything. That's just a function call. In other words, control goes into the thing that you're awaiting, and then it comes back to you afterwards, right? Actually, the only reason that you need to know about it at all is if it was possible to re-enter the same data structure. But that conflicts with value semantics, right? So if there's no re-entrant mutation, which we rule out, there's no point there's absolutely no point in saying those things. So I wasn't into all that noise. So we ruled out function coloring, which means that we have a stateful coroutine model. We want to use ordinary function composition because it's there in the language, as opposed to what? Well, senders, receivers. Now, senders, receivers is a great technology, and it even can perform better than some of the stuff that we've done so far. But it requires letting go of your usual idiom for composing computations and using these expression templates. There's still room for that in Hylo if people want to do that, but we wanted there to be a bog standard thing with excellent performance built on just the language mechanisms. And Lucian has produced some really excellent results. Obviously, we're leveraging value semantics for thread safety and trying to avoid excess synchronization. I don't know if I have time to go through Lucian's slides. So, 2 minutes. And that wasn't supposed to happen. Okay, we can do that. Okay, so we have a model based on spawning futures, and there's sort of two categories of thing that come out of that. There's strictly structured concurrency, where your futures don't move. They never escape the function that they're spawned in. And this has more structure, less flexibility, but one thing it does mean is that the futures can access the local stack. And it's faster. It means that no dynamic allocation has to happen for the coroutine. Then there's weakly structured, where futures actually can escape the function, and we need both. Definitely some of Adobe's applications need weakly structured concurrency. That you can't access the local stack, and it does require allocation. One of the beautiful things that has fallen out of Hylo's model is we track which things are escaping in such a way that it's just in the type system. We can tell which one you're doing without having a separate, there's no separate APIs for weakly structured and structured concurrency. If you return the future, you're weakly structured, and the type system just does the right thing. Okay, the last bit that I'll show you is if you have a task that goes ABC and it spawns C, ABD, and it spawns C. That's what we've got here, right? It could execute like this, but it could also execute like this. And if it executes like this, the normal thing to do would be to block thread 1, and we don't want to do that. So instead, we have what's called thread hopping, where thread 1 goes and executes T2 continuation, some other available work, and then D finishes on thread, my mouse curses over, 2. So that's an extremely efficient model. It causes certain challenges for interop with other systems. Like if you're a callback for some C library, that library probably wants you to come back on the same thread that you were called on, and we'll be surprised. So we have a mechanism for dealing with that. It's a trade-off that costs a certain amount of efficiency. If you happen to have thread hopped, you do have to block. Okay. I think we're out of time to do these other things. Huh?
Just do this slide, I think.
Well, I thought, do we have time for questions? Are we going to take
Time for questions now.
Okay, so, I've shown you a lot that's like Swift. So, oh yes, I never fixed the animations on this slide. This is all backwards. Okay, so the first point is supposed to be, one of our key advantages is 20/20 hindsight, right? I have to give a lot of credit to Swift. It's very easy to make better decisions when you come second. Swift didn't start with move-only and immovable types in the system, and everything was assumed to be copyable. And therefore, as they started to put those features in, it's a similar experience to C++. The defaults are wrong. And pass by value in Swift still makes a copy. That's not as expensive as in C++ because all dynamic data structures are copy on write, but it's still too expensive. And so the implicit copy semantics is it's a trap we didn't fall into. I mentioned function coloring. Swift has that problem. Rust has that problem. The last thing I want to mention is I think Swift has kind of a priorities problem. And like in terms of, the whole fundamentals first thing that we're trying to do, Swift may have lost sight of that. Because that modify accessor that I was showing you, that's been in the implementation for years now. It's like the key to efficient value semantics. And it has not ever been officially put through the evolution process. All they need to do is put it through the evolution process. That's the reason it has that leading underscore, okay? They just need to put it through the evolution process and document it. And then it would be officially part of the language. But instead, other things are taking priority, like macros and other kind of highfalutin things that, are not the basic model. Okay, that's my criticism of Swift. I'm not going to do any more. Thank you all very much for coming. It was fun talking to you.